to September's meeting of the Astronomy Society of Frankston. Well, welcome, especially if this is one of your first times along to the meeting. My name is Skilton, and the order of the meeting is usually a talk up front that will go for anywhere up to about an hour. Then we break for a tea break next door for about half an hour, and then we come back into two parallel sessions. One is in here being open forum, and on at the same time is video next door in the library room, so you can make your choice at tea break. Now there are quite a few things on tonight and quite a few things being handed round. The what's ons are going round, the raffle tickets are going round at the moment. If you wish a raffle ticket, they're $1 each. Marty's also put in some tickets for some charity, Marty. What's that? For SIDS. So if you wish to donate, I think they're $2 a ticket to that, please do. It's coming around in the raffle ticket one. I'll also hand around the usual idea, question, suggestion box and the viewing night roster, because we have two more public Mars viewing nights this coming Friday night at the Briars and the Friday after at the Briars. So please, if you can actually do those, put your name down on the roster sheet and pass it back, so I'll put that through. We currently don't have any telescopes for those at the moment. I'll give you a few moments to absorb that one before I hand around the next one. Right, the treasurer tonight is Marty Rudd, who's about to put his hand up in the air at the back there. If you're looking for the treasurer to relieve you of any of that hard-earned cash. And he's at the back, and you can catch him during tea break or any time after the meeting. Remember name tags, please, if you can. It helps newer members to identify who you are, and it also helps we older members who are losing our memories to remember who you are as well. Particularly as we've got so many members, it can be a bit of a strain at times. Congratulations to the following people for having achieved various milestones. 3-year membership milestone goes to Tanya Hill, the planetarium, Mark Hillen, not sure he's here tonight, and Ian Sullivan as well. Congratulations on reaching 3 years. And newer members, Marcus Brilski, Ashley Cameron, Maureen Canning, Anna Gates, and Varna Amarasinghe as well. Any of those here tonight? No, none tonight. Okay, so we march on. Thanks also to Heinz Rummel for donating tonight a Messier poster. He's just been over to the United States and he's donated that to the Society for laminating, and we can put that up on the wall. So thank you very much on behalf of the Society. And that was in a rolled up tube that Bruce had somewhere. At the tea break, Andrew Thornton's the librarian. He'll put his hand up there if you're looking for the library, and which is round where the videos will be shown. And if you're a financial member, you can certainly borrow anything from the library, books, CD-ROMs, or even the loan telescope or binoculars. Now the What's On handouts have gone around. Right, now since the last meeting, we've been absolutely run off our feet with viewing nights. We've had Year 3-4 Summers Primary School, which had about 50 people turn up for that one. We had Blackrock Primary School, Year 5, about 50 turn up for that one. Virtually no crowd about those occasions. We had Seaford Primary School, Year 5-6. They were a bit of a rowdy lot, and also the first time we ever did that school. And we had about 55 turn up for that, including the teachers. There was a minor amount of crowd on that, but we managed to cope without any problem. We've had a number of Mars nights for the general public. There was one on obviously August 22nd as part of National Science Week, and we had about 150 turn up for that one, so that was a fair turnout. On August 29th, we had another public night. We had about 60 turn up, and that was about 3/4 covered in clouds, so we did quite well to get 60. September the 5th, we had about 100 turn up with widespread cloud across most of the metropolitan region, except for the Briars, where the clouds opened very nicely, and they were very clear viewing all evening for those people who did turn up. Last Friday night, if you recall, was also raining. The Mars night at the Briars, September 12th. Saw about 20 turn up and the rain cleared and they had perfectly clear viewing, and in fact I have to say it's one of the steadiest views I've seen of Mars this apparition, so they were very, very lucky. The rain beforehand settled all the dust out of the air as well. So we've had quite a lot of viewing nights in the past month or so. Member nights, any to mention?
Well, actually things have been fairly quiet with member nights recently. I haven't gone along to anything because I don't think, there haven't been any that have been poorly attended simply because of the poor weather we've been having recently. And of course Peter's already described the very well attended public nights we've been having. As he just mentioned, we've got 3 public nights coming up on the next 3 Fridays, so we'd like to see some attendance there. People coming along to help out with telescopes and other help. Also, as mentioned in the What's On leaflet, the Telescope Learning Day won't be happening next month because David Girling is unable to run that, and we haven't been able to have anybody else to run that. And also, as some of you may have seen already, Peter Skilton made front page news in last week's Peninsula Weekender with an article on the Society. Also, a further 2-pager. I'll be pinning up a copy of this article at the Briars in the future. And finally, for those members who haven't been to the Briars before, I've brought along some copies of maps of the site for those who need help getting to that, and I'll put them out over there later.
Thanks, John. Right, astronomy classes. Ian, you want to say anything on that?
Yes, the next class will be this Saturday, that's September 20th. If you are interested, please see me tonight at some stage and a little afterwards. And if you're new, that's okay. If you have been before, perhaps you could acknowledge that you're coming. And so we know we'll be right. But it's the Mount Eliza Community Hall, which is in the main street of Mount Eliza. The one after that looks like being Saturday, October the 25th, which will be after the next general meeting. These are theory classes. It's not telescope learning. Theory classes, starting virtually at the beginning, things like celestial sphere, solar system, understanding the principles involved that we don't have time to explain generally, not in the same detail as the general meeting. That's the idea.
Right, now the first wave has gone around the handouts. We have another handout here. We have 2 visitors tonight from Benja, and we have Jason Beatty, who will put up his hand so that you can see roughly where he's sitting. He's doing his honours year at La Trobe University, and he's put together an astronomy-related survey as part of that course. And I have a number of surveys to actually hand around to people, so I believe it takes about 10 minutes. It's a simple multiple choice questions. If you don't have any objections, please fill them in as honestly as you can for Jason so he can take them away. Also sitting next to him is Julie Nelson from Bendigo as well, and they have a bit of a trip back tonight, so we'll try and do this as quickly as possible, so please don't leave it to the end of the meeting. So I'll hand them around now, and also to the pens that Jason's brought down. Please return the pen afterwards. We don't want to get a reputation. On your What's On handouts, James just pointed out that the working bee date shown is incorrect. It should actually be 7 days before that one. So instead of October 12th, it's actually October the 5th. So if you can please amend it as the pens are coming round, show that. Right, lunar grazers. There have been none in the previous month that were favourable, and indeed there are none planned for the coming month. Predictions of the eclipses of Jupiter's moons have arrived for 2003-2004. Those of you who are on email on eScorpius would have access to them in the files section. There's a file being uploaded there of all the prediction details, so you can watch the moons of Jupiter disappear before your very eyes. Minor planets, there are no minor planet occultations in the upcoming month. However, the recent Alcesta occultation of Vega Virginis, which is a very bright one, the final results have come in for that, as well as the one that was done about a month later of Benja Minor. This was done across the state, and this is the outcome. Now, this is the result of all the astronautical societies teaming together on this one. And the first one was Alcesta. Now that was the one that was plagued by a lot of cloud down here, so a lot of our observers who didn't travel tended to be under cloud. Frankston on here would be down around here. So you had to actually travel up to probably around Mount Wayfield way to actually get in. From about there downwards was actually thick cloud, so it's no wonder none of our observers who couldn't travel got that one. I think I was that line there, so it missed me. I went too far. Now what's shown here is the size and shape of what the asteroid was, whose shadow came over Victoria. And every one of these lines along here is actually one of the observers sitting on the ground looking at the background star. When the shadow came over them, the star disappeared for that length of time. And as you can see, you can get a fairly good idea of what the asteroid looked like at that moment as it came over. And it was about 70 odd kilometres by 60 kilometres wide, so a bit bigger than Port Phillip Bay. Now the next one that was done about a month later, and these were fairly bright stars, which is quite unusual, so you can do them even in binoculars. That first one was a binocular object, you could do it. Next one was the asteroid Benja Minor, and as you see, similar sort of deal here. I think my one was around the middle. And that's around the 80 kilometres by 40 kilometres, so a bit more elongated, that asteroid. So you can see this. Sorry?
Where were you there?
I was one of those.
No, where were you?
A place called Baralmo, which is halfway to Euroa. Half between Melbourne and Euroa. Right, so a little way off. Now, there's something of interest with another graze that's coming up, and this is of Mars itself. So Mars will be grazed by the Moon in a couple of weeks' time. I'll see if I can show you this. Now, this obviously is a map of Port Phillip Bay, and you should be able to make out Frankston down there, and going up to around Mordialloc and Mentone. And that red line, or if you can't just make out the colour, that line going there is on October 6th, 7th, the night of the change of those, at about 2:36 in the morning, for those that are keen. If you're positioned anywhere along that line, what you will see is the planet Mars grazing along the very edge of the Moon. So it may or may not partially or wholly disappear because it gets hidden behind the mountains of the Moon. So those of you who are astrophotographers or can get a video camera on it, please do try it, because grazing occultations of planets are extremely rare and spectacular. If you want further details of that, I'll certainly send around more detailed coordinates on East Scorpius. But that gives you an idea that if you pretty much go to Springvale's virtually on it, Scoresby's on it, halfway between Mordialloc and Mentone is on it. Right. Member observations. Are there any members here who have any observations of note? Have any of you seen anything noteworthy in the sky in the last month that's big and red, maybe? Hint, hint. Unfortunately, I didn't bring my laptop tonight, but some members have been attempting photographs. Unfortunately, they don't turn out too well when they're printed on ordinary paper. So,
turn the lights down a bit.
now, this one was actually tried after one of the school nights by Paul Taylor at the back there with his brand new handheld digital camera. And he just took the Society's Lone telescope and pointed it through the eyepiece, nothing fancy about that. And actually, at the time of that snapshot, that's the face showing Mars there. If you can imagine that sort of turned into a circular object. And that's what he snapped with the digital camera there. And unfortunately, the printing doesn't actually show it, but on the screen, you can actually see 3 dark markings there that correspond to these 3 dark markings here, and also a darker area down the bottom, and also a slightly lighter area at the top there. Unfortunately, it was a little bit smudged because it was with the Dobsonian telescope unguided, so it's just sitting there with the Earth rotating it around, and also the camera was handheld against the lens and just went click. So you did very well with that one.
Very scientific.
Very scientific. Those on email would have seen David Gerling's one with his 14-inch. Shown here, and again the print doesn't do a justification, but dark markings there at the polar cap, again with a digital camera but mounted on a more substantial telescope. And since Jason's here tonight, I've also shown his. Again, doesn't do justice to it because of the printing, but it's got a good dark region there. I'm not sure if that was Certus Major. It looks, looks a little bit like it. And the South Polar cap up the top as well. And that's with a 10-inch with ordinary photograph, isn't it? Ordinary 400 ASA film. And my 2.5-inch refractor.
Wow.
Well, maybe not. Right.
It was a homemade one too, wasn't it?
With an Instamatic camera. Yes. Right, there have been no aurorae reported during the month, and I'm informed that we might have something on a program called Postcards.
No, you won't.
You won't? No, in that case, I haven't been informed that. Right, as mentioned last time, the next National Australian Convention of Amateur Astronomers is scheduled for Easter next year, which is April 9 to 12. And I believe they are taking bookings already. It's at the Rest Point Hotel, but just early advice for your diaries. Okay, well I think with that we might ask Peter to come up and do you need the lights up, Peter?
No, that's all right.
Peter Norman is virtually a lifelong member of the Astronaut Society of Frankston, one of the earlier founding members, and he's been president for more years than even I recall, probably double what I've been. The longest standing president the Society has had, and he usually attends all the Vastrops and NASAs that he can get to and beguiles them with very, very complex talks on subatomic physics and origin of the universe, and I look forward to being beguiled tonight. Thanks, Ben.
Thank you. Thank you. Tonight, just a rough rundown of where we've been, all our atoms, since the universe began about 14,000 million years ago. So it's a quick run of what happened, but what was most important about it is that we've recently, or we haven't, NASA has recently this year taken a lovely photo of the Big Bang using very sophisticated satellite circling the Earth or searching the sun, I should say. And I'll give you the details of what they've seen. We love fireworks. We look out in the sky and don't see too many happening. It happened a long while ago, about 14,000 million years ago, but they've still taken lovely pictures of it by radio telescopes. And I'll explain how it goes as we go. If we think back to the 1920s, there was a pipe-smoking American Rhodes Scholar from Oxford was given charge of the newly built 100-inch telescope in Mount Palomar, or wherever it was, overlooking Los Angeles, and he looked out through this brand new telescope and looked at distant galaxies, and he found a remarkable thing. The further, they were all running away from us, and the furthest ones were running fastest from us. And this is when he plotted up his data what it looked like. And it's called a red shift. The light from them, the fringe lines, the spectra, were shifted towards the red end. by the Doppler effect, the same procedure by which policemen are able to tell you how fast you're going on the road with one of their ray guns. In this case, the telescope is the ray gun, picking up these quickly vanishing nearer, and this is the speed at which they're disappearing. The nearer ones, galaxies like M31, Andromeda Nebula, are fairly close, and they've got a very low redshift. But the further away you go, you get them disappearing. And people have been able to measure redshifts of different objects for the last 80 years or so, further and further out into space as telescopes increased in size. And so we every now and then see in the paper that they've just discovered another galaxy with a redshift of perhaps, if that's 1, then a redshift of 4 or 5 or something like that.
The horizontal axis is velocity.
Yep, this is velocity here, speed, and it goes from 0, the nearest things, ourselves, to the speed of light, where we can't see anything. Or you can take, it tells you the distance of the picture we see of the universe, or the actual map of where things are now, which is twice as far away. And then you can work out here the slope of the line, which gives you the speed at which they're vanishing from us, and that helps us by tipping it upside down to tell us how old the universe is. So measuring, plotting this graph of distant galaxies and so on is important. Now what we want to know is, the Big Bang occurred right over here. We can see, or we should in theory see the remnants of the Big Bang almost on the right hand side here. And as I'll show you soon, the latest data from this observation of the flash of the Big Bang has a redshift of about 1,000. Now the most distant quasar ever observed has only got a redshift of about 7. So this new technique they've got of observing the Big Bang
What's that
flash,
one? What's the one though? What's
the 1 is a redshift of 1. And
1 what?
just 1, it's a number. The redshift is the change in wavelength. It's lambda 2 minus lambda 1 over lambda 1. It's a change in wavelength due to the redshift of the distant object.
So what?
It's a ratio, just a number, no units.
the ratio of one over the other?
Yep. The difference between
There's
the...
no redshift, it's 0, isn't it?
That's right.
And if it's 1,
Then it's moving it. The old idea was that if you measure the redshift of 1 in classical mechanics, it meant the object was moving away with the speed of light. But we now know there are objects out there with redshifts of 7, 4, 5, which means they're travelling faster than light, which is impossible unless you apply the special theory of relativity, which gives this curved light. All right? So it's only explicable in terms of special relativity. Good. We won't dwell upon that. It's an introduction to what we're about to observe, what happened to all of us, or rather just our atoms. We probably didn't have much of a mind in those days. This is another diagram of that thing. The universe started with a Big Bang down here, and suddenly it inflated 10 by 10 by 10 by 10, 10 to the power 50, 10 by itself 50 times. Suddenly it inflated when the universe was very exceptionally young and stretched enormously by inflation until it's still out here expanding now. And this axis, this is time. This axis here is the width of the universe, or any length measurement in the universe. So everything gets further apart. These are the distant galaxies right out on the boundary of space. This is us here, looking out and observing them across into the unknown, as it were. So that thought we'll come back to with some more meaning later, but it gives us a start. Now, the details of this I'll go through quickly. I'm legally blind, so I can't read them, but you can. So it began in this theory, T equals 0. It had a Big Bang. Everything was squashed up together. It was just a foam of space and time all mixed up. And gradually it sorted itself out very quickly. Gradually, very quickly. When the universe was 1 divided by 10 times itself, 43, that fraction of a second, which is a very small portion of time, it was the Planck time. At that time, these things happened. GUT means the grand unified theory, when everything was all squashed together. Gravity was mixed up with light, was mixed up with the weak force, was mixed up with the strong force, etc. And slowly things pulled apart. And the world as we know it, this is the story, it's current mythology, you don't have to believe it, it's just our current storytelling. And as time went by, very quickly, in those early days, different parts of the universe unfolded and eventually ended up like us sitting in this room. Here, the millionth of a second, this is what happened. Here, at 10,000 millionth of a second, this happened. We had quarks, some of the minute particles which matter, such as protons and neutrons, are made. They start to form and isolate and combine. We get here to a millionth of a second, when the universe was that old. The size of it was what here? Very small in size. Yes, it certainly was. And it got bigger after that inflation, which was quite early in the piece. And then, on the last page of this detailed explanation about history, 3 minutes, that happened until we get to this stage here. About 300,000 years after the Big Bang occurred, for the first time, light was able to travel in straight lines. Up until then, everything was just like being inside the sun, a right royal mess. Everything was, there were no neutral atoms, everything was charged particles, like living inside a fluorescent light. Not very interesting, you couldn't see anything anyway. And till that time, when it cooled down to 3,000 degrees, which is about half the temperature of the surface of the sun, when it cooled down to that temperature for the first time, electrons could whip around protons and form neutral hydrogen atoms and got them neutralized. And these neutral atoms for the first time allowed light to pass through and see things. And that light which was formed when the electron combined with the proton to form the first hydrogen atom released a lot of ultraviolet energy, a huge flash of the Big Bang. There was a lot of flashes before that, but you couldn't see them anyway. Everybody was just drowned in this violent energy field. But for this time, that energy was able to be released and travel out through the gas of the matter of the universe. And that energy is called, at that time, is called the decoupling between light or ultraviolet or any electromagnetic radiation and matter. And that energy released is what we now see with radio telescopes as the aftermath of the Big Bang, like the fireworks display at morning. And you don't see it now as bright ultraviolet light. This is a rough history summarised. Again, that same picture, the Big Bang down here. Suddenly, violently, everything expanded enormously, 10 to the 50 times, and then went on its happy way. And as things cooled down and expanded, this mess down here would suddenly sort itself out into galaxies, stars, clusters of stars, planets, you and me. Now, it's about here, this time here, about 300,000 years or 380,000 years after the Big Bang, is when this decoupling between energy and matter occurred, and that's what we are now able to see as the remnants of the first visible flash of the Big Bang. Now, we are able to see it not as ultraviolet, but as radio waves, because as the universe expanded after the Big Bang, it cooled down, as I put on the notice on the sheets before. The temperature of the universe and everything in it dropped. And it dropped quite dramatically, from 10 million billion degrees Celsius until it got down here to decoupling when it reached 3,000 degrees. And at that stage, electrons and protons and things came together and formed neutral atoms. Now since, and this is a logarithmic scale, since then until now is really a very long time. It's certainly very nearly about 14,000 million years. But in that time, the temperature has cooled down for all of that radiation released in the Big Bang flash. It's cooled down to only 3 degrees Kelvin, 3 degrees absolute, minus 270 degrees Celsius. And here's the time scale as we said before. So that's another way of representing this time scale we're talking about. Now, although they realised that the universe had begun with the Big Bang back in the 1930s and 40s, no one had thought that you would ever be able to see the flash of that Big Bang, except Gamow, who was the first person really to think and talk about the Big Bang as possibly being our origin. And he said, well, roughly speaking, by the graph I just showed you, if you accept the cooling and so on, the temperature should be of that radiation around us should be about 10 to, the redshift gets down, it should be, I've got a temperature there, yeah. 5, is that 5 degrees Kelvin?
Yeah.
Temperature should be 5 degrees Kelvin, which is about minus 268 degrees Celsius. He just made that rough estimate, but he never thought you could ever hope to see it back when he wrote about that in 1945. So no one ever bothered to go and look for it. He didn't send out parties to go and look. And it was really only before we described the first accidental discovery of this flash, let's quickly remind ourselves of the nature of light and radiation. Here's the hydrogen atom, an electron buzzing around it. And it depends how close to the proton the electron is, how much energy is released in radiation. When the electron first combined and orbited around the proton, it released ultraviolet radiation. And we know from our memory of optics that light is in the form of waves. Some people talk about rays, straight line. Well, really, we know it's electromagnetic waves. And they've got a wavelength, a number of, they travel at the speed of light, 3, whatever it is, 100,000 kilometres a second. And that means they have a frequency also, the number of waves per second that passes. If we think again of that spectrum of light, or other electromagnetic radiation, we can think of the most energetic forms up here. Gamma rays, the death rays of atomic bombs, have very high frequencies, many waves per second. Very, very short wavelengths. Shorter than a nanometer. A nanometer is a billionth of a meter. An ultraviolet has a bit longer than a billionth of a meter wavelength. Come down here to microwaves, which you get in the microwave heater at home, or microwave radiation, which we're going to talk about in a moment. They have frequencies in the range of gigahertz, that's 1,000 million hertz or vibrations a second. Is that right? Yeah. And down here. Okay. So that's the spectrum we were talking about. And what happened was, the Big Bang, the radiation left the Big Bang 14 billion years ago as ultraviolet. It's been redshifted 1,000 times, and what's now out there, all around us, everywhere in the universe, as microwaves. Well, if you want to look at radio waves in the sky, I put this in for fun. Back in 1977, some amateur radio hobbyists at the Ballarat Astronomical Society built themselves a radio telescope, stuck an antenna on a couple of power poles in their astronomical yard, and out here's the shot at night, that's in daytime. And they had a radio shack there, and they scanned around the area and measured the strength of radiation coming from the sky. That's irrelevant, that's in they plotted their results in this manner. They weren't looking for a relic of the Big Bang, they were just seeing what they could see with their local equipment. And they plotted this view of the night sky, their plot of various intensity lines of the night sky. Right ascension and declination coordinates. Some parts had more radiation than others. What frequency did they use? 135 megahertz. Megahertz is 1 million vibrations a second. That's typical TV frequencies. But they should have been looking, if they were looking for microwave radiation, in the gigahertz. There's billion waves per second. Well, how was it discovered? By accident, as most good scientific discoveries are made. And here, this is a lovely telephone, a radio telephone, owned by Bell Telephone Company in America. And they built it specially, tiltable horn which could be pointed to a particular point in the sky or anywhere you like. And it was used to improve their international radiation communication Bell Telephone Company. And what they did was, to improve their overseas communications, it was in the early 60s, so just after people, or even before they went to the moon, of course, but rockets were going up. And they very cleverly launched a huge reflective balloon high up in space, and they had it in a stationary orbit, and they were bouncing radio messages off this shiny balloon to other parts of the world. It was a smart way of sending telephone messages across from one part of the world to the other.
Not the echo balloon.
Yeah, the echo balloon, back in the early 60s. And it wasn't very smart. Before long they had satellites up here which we now get our weather maps from and all those other things in our international communications and television and radio take place by and telephone. And so they no longer needed this lovely radio telescope. So a couple of the guys on the staff at Bell said, hey, fellas, if you don't need it, we'll use it for some amateur radio astronomy. We're going to have a really good squint at radio galaxies and quasars out there. But before they went to look at them to get the details, they thought we'd better calibrate this instrument and see that it's all clean and the amplifiers are clean and not noisy, everything's working. So they took a random squint around the sky, every part, and to see what noise was in the atmosphere, what noise was in their aerial, more importantly, what noise was in their amplifiers. And they found there was noise there which they couldn't explain. It shouldn't have been there. It should have been quite silent, no background hum or noise at all. And in desperation, they sort of wrote it up in a journal, and somebody twigged what it was. They were picking up the flash that was left over of the flash of the Big Bang about 14 billion years ago. And they suddenly twigged that by accident they discovered the background radiation. One stage, they were even so concerned that the noise was there, they thought it was coming from pigeon poo, from a pigeon's nest, and they cleaned that out. It didn't make any difference either, because it was coming from the universe. And this is their plot. They got a very uniform radiation, which they measured to have a temperature by redshift of 3 degrees absolute, minus 270 degrees Celsius. And very uniform. That upset the cosmologists, because they said, no fellas, if that was the flash after the Big Bang, there should be some detail there. Because after all, you and I are detailed, the stars and galaxies and everything are detailed. And if God made a uniform universe, it'd just be a mess of dead, dry hydrogen gas, nothing interesting at all. So they said, look, it's all very nice, fellas, you got the temperature right, near enough. But we want to get a better look. So they started building bigger and better tank telescopes for exactly that purpose. And this is again a brief reversion to what we were talking about before, to the fact that this is a plot, it's a Planck radiation, black body radiation diagram of what they actually measured. We'll see more details of it later. This is wavelength, this is brightness, or energy per wavelength. This is the sort of plot you get from a mass of gas in a container at 3,000 degrees Celsius, as it would have been in the universe when that energy was first released 380,000 years ago. It has cooled down from 3,000 degrees when that wavelength, the maximum wavelength, is that many centimetres, very small, because it's ultraviolet. And now you would expect it to be a temperature of about 3 degrees or near enough. And this is what those two fellows, Benja and Wilson, with their big radio telescope measured. They drew this plot, much bigger and better than that one, and they got that curve, which told them that the temperature of the radiation is now 3 degrees. If that's the case, it has a wavelength of about that. Now you can measure the redshift we were talking about before. Here's the formula. The wavelength of the energy as it arrives, take away the wavelength of the energy when it left its source, the galaxy or whatever, in this case the Big Bang, and divide it by the wavelength of that amount. So that's all redshift is. It's a difference divided by the, like we get percentages, I think, just a fraction. And it comes to be, if you do that, 999, or near enough to 1,000, the biggest redshift people have ever been able to measure. So that's an explanation of what they got. That little plot, that little curve told them all they needed to know. So they got stuck into it, some of the people with a bit of money and government backing. And this fellow, Smoot, interesting yank, very enthusiastic and energetic, he conned the government into sending up this machine back in 1991, was it? 92. And it's got these solar panels for energy. It's got a big sort of a gold shield underneath it to keep the sun out, and aimed it out into the sky away from the sun as it circled the Earth. And it took radio messages for quite some time, and eventually got this picture. And it showed, when they worked out the details, that in fact the temperature of the background radiation was 2.73 degrees Celsius. Not bad accuracy. And these are very minor, don't worry about the middle bit, these are very minor variations of the temperature of the remnant radiation that's still out there after that Big Bang. And they still weren't satisfied. But before we get to be dissatisfied, everyone was very pleased. And Mr. Smoot was so pleased that he published this big book about wrinkles in space-time, which that map shows must have existed very shortly after the universe was begun because of irregularities in the quantum state of the early universe. There's Mr. Smoot, very smooth looking bloke. That's where I got some of the pictures from. Then, this is one that was pictured, one of his pictures, and not in colour, published in, what's that, New Scientist, is it? News and Views. Must be the physicist. The English physicist.
No, it's Nature.
Okay. So, then the Yanks are never satisfied, so they built a bigger and better thing in early this millennium. 2001 they got a Delta rocket and carted up an even bigger and better machine to have a squint at the universe with greater detail, because we want to know how we began after all, and know what it was like. And this is what they did. They sent this machine up into space. Here's the sun, here's the Earth, here's the moon. They send it out into an orbit, which is a special Lagrangian orbit. Here's the sun, here's the Earth, here's the moon, and here it is. And it stays at that point called the Lagrange 2 point, and it circles with the Earth around the sun once a year, always pointing out away from the sun, which would only confuse it. It's got that big gold reflective shield to keep the sunlight out. So all its trinkets up there, very specialised equipment. Sending back very detailed measurements of Earth, and they were able thereby to plot this image. Much more detail. That's how the universe looked 380,000 years after the Big Bang, all those little lumps and bumps. They measured it to an accuracy of 1 part in about 100,000, the temperature variation from point to point, great accuracy. This is another picture of the equipment they used. This, you can all get this from the net. Just type in WMAP, Wilson Microwave Anisotropy Probe, and you get more than you need. Hundreds of pages of details and colour pictures. That's their map of it. Now, the question is, what does that tell us? Well, just one more look at this machine before we leave it. It tells us this, like we've been saying all along. That was the Big Bang, and this was 380,000 years after the Big Bang. Then that's what we're seeing now by the use, and this here it is, in the full glory, lumps and bumps all over it. Now, if you analyse all those lumps and bumps, you can find out something about what the universe is made of. And this is the last three overlays just to tell us what it tells us. Still, pardon?
Excuse me, Peter. How that diagram that you just might held up would appear to be an all-sky measurement.
Yep.
How did they subtract the effects of the Milky Way?
Well, they do that. I'm not an expert, but they do it. Yep.
Compensate from some way.
Yeah, they cancel out everything that's known and other previous. Wouldn't have made any difference. I was there, wouldn't have made any difference. I'm not much good. Anyhow, what they plotted was this. They got that radiation curve, a Planck distribution for energy, that proved quite categorically with its perfect shape over different wavelengths, the brightness of each wavelength. That was at a temperature, the radiation now has a temperature of 2.735 degrees Kelvin, and these are some of the details. Papers isn't good there. But if you've got good eyesight, you might be able to read some of that. Told us the temperature. Told us of the details of that graph that had happened about 380,000 years ago. It was a redshift of 999. Tells us that, what's that say? 1 part of 100,000 was the accuracy of measuring with that radio telescope of the temperature of the flash from the Big Bang in microwaves. And down here, they're developing new techniques, including measuring polarization, which tells us something else yet again. And there are about 6 other projects, land-based ones, around the world. We've been looking at this for the last 10 years, trying to get a better handle on where we came from and what things were like in those early days. And this is another analysis of that spotty graph we saw before. This is called an angular power distribution graph. And that fancy jumps and bumps tells us all these things. We need to be well into this stuff. I'm certainly not. I just summarise what I read. I tried. That, in effect, the universe, as we look around us, we're only a very small part of that universe. The sort of matter we see in stars and galaxies really only constitutes 2% of all the known energy and matter in the universe. What's the other 98% of the universe made of, if it's not made of the 92 elements and all the radiation which we're familiar with? Well, that's the open question. Sometimes we think we know everything. The more people learn, the more we learn we don't know. Here it is. This is a summary of what we're made of, what the universe, not me personally, but what the universe is. You and I, and the stars and stuff, 2% of the universe are made up of ordinary matter, protons, neutrons, electrons, okay. Got mass, give out light and so on. Then there's dark matter, invisible matter, which is made up of these things. Protons, etc., ordinary matter, but it's so far away, so small, we can't see it. It's invisible to our present measuring, although people are still looking up there for these machos, the massive things from the halo, massive condensed objects from the halo, ordinary matter, but not currently been measured or observed yet. It's got to be there. Then there's dark matter. Dark matter is matter which we don't know anything about yet. Some people think that perhaps neutrinos, which billions of us are zapping through us at this moment from the sun and outer space without doing anything to us, going well through most of the Earth. We've always thought they're a bit like light particles, they don't have any mass. But we now thought that there's mass. If neutrinos have mass, heavy neutrinos, then they could account for some of this 23% of an unknown matter out there. Or they could be axons, God knows what they are. Or they could be WIMPs, weakly interacting massive particles, God knows what they are. We've got all this ahead of us to find out, so get out there, go out there and find out what it is. And as for dark energy, which is 3/4 of the universe, God knows the fact what that is. So there you go, that's your puzzle, go and find out. Best of luck.
I'm sure if any of you have any questions, Peter will be more than happy to answer.
Just yesterday I read something about called the electric cosmos.
About what?
Electric cosmos, which is sort of plasma physics, which discounts Big Bang, black holes, WIMPs, machos,
Right.
neutrino, whatever, all the phlogiston that's in astronomy. This theory, I haven't really read it in detail yet, but it seems to discount all of that.
Well,
Do you know anything about it?
no, but everybody's allowed to have their own theory. And the
Well,
world is full of
this points to some of Alton Art's work on quasars and galaxies, the contradiction of the blue and red redshift of associated objects. And this electric cosmos seems to deal with it in a different way. I was wondering if anybody else has heard about it.
I once went to a week-long cosmology conference at ANU in Canberra and thought I knew a bit about cosmology before I got there. I smartly learned that I didn't. We had 5 international lecturers giving us an hour's lecture each day, filling a roll of blackboards as fast as they could write, and each of them started with a different set of equations, and none of them came to the same conclusion. Now, they're the experts. What I've tried to tell you is what I think might be reasonable and might last in time, with the passage of time as being vaguely universally acceptable at this moment. But tomorrow, the day after, other people have other people. This is just current mythology. It's not true.
Any other questions?
Supper time.
Yeah. Peter will certainly be around for the rest of the evening if you wish to ask him questions offline. Right, are the record ready to go?
It hasn't come here.
Didn't get up there. Did anyone want to buy a raffle ticket and get an opportunity? Now's your opportunity. With the surveys, can you please hand them to Jason on the way out as well, please? We're going next door for the tea break. Now, what we'll do before we all leave, we'll draw the raffle, and then we'll go out for a tea break and reconvene in here at 9:30. And remember, there are 2 sessions on. There's a session in here at Folk Hill, we'll be talking the sky for the 9s. Ian Sullivan's got something on Mars. And next door, the video is on Space, the Final Junkyard, and it actually features someone in there that visited the Society about 4 or 5 years ago, Paul Maley from the Johnson Space Centre. He's actually in this particular video. So the video will be starting sharply at 9:25, so as to give it enough time to run through the entire length. All right, we are ready to go? Is there anyone else here who wishes to bring up anything before we just draw the record?
Yeah, just quickly mention that I've got about 24 of these name tags to give to your members who haven't already picked one up already yet. So if you've got a name tag, just come and chase me up at some point, please.
So what's the first one?
31.
Number 31 is the first one, his first pick. Which one of the three would you like?
Next number's 13.
Second choice. And the third one is 30. Congratulations on those things. Okay, well if you're new here, just follow the rest of the crowd next door to the tea room, and as I say, we'll reconvene in here at 9:30. Please hand your surveys to Jason on the way out. Indian Ocean. It's actually on. It's well spotted. The strip map on that Mars actually shows this feature and you can see in this picture that on the website, and that's half the sea background, which This is coming from Johnson, it was 23. So the notes got there from the smart. Okay, so they're from the city. Okay, so that's the 19th.
Thank you much, Lee.
Right, thank you. Thanks very much. ASV and ASM were pretty much the only ones that got back to me.
Oh, okay. I would look over it.
Oh, 50.
You're honorary baller, aren't you?
And Gippsland did, you're likely to get a response from this, mate. Well, you didn't get a response.
It was just about getting wrong.
Yeah. Gippsland not going very well.
I dare say the way we used to try to change to the content details change as well.
Yeah. At the end of every year, I have to keep on the planetarium and the rules and contracts over this thing. Their details get out of date. There's no rules. Details to the public. You get disarmed. They make comments all the time.
Yeah, exactly.
Yes, and what's the in Bendigo? They've got president, secretary, treasurer, and things like that. And what they meet at what? At somebody's house or?
At the brick hotel.
So, I see. And people give talks.
Occasionally.
Yeah, but otherwise just to talk. And occasionally somebody gets invited to someone else applies to the telescope.
Yes, yeah, they
Do you have
they
nights
don't-
for Mars, did you? Do you have any nights for Mars around the town?
My backyard was buzzing.
Yeah, Joe's got a telescope, yeah, take photos.
Yeah.
No,
You did very well, actually.
Didn't
Well,
advertise
not
anything for...
And the ones that turn out
No,
I'm not with the public.
Oh, no, I see, yes.
The other ones I was using a bar light.
That's our individual.
Yeah.
I thought, yeah, I'm getting some great shots here.
Yeah, I was the
Just
secretary.
How detailed did you scan that one? Was that 2000?
Yeah,
2000 dpi.
Because there's a bit of software that I hunted up recently, was 2 bits that deblur images via deconvolution.
Yep.
So they basically search for the patterns. And I went to a lecture at the University of Geelong, lectures of physics, and they had this guy from the Road Transport Authority, and they use similar sort of software on the speed cameras. So the speed, even though the thing happened to be blurred because this person's doing say 200 across the field of view, basically put it through this application, and the number that comes out.
Yeah, definitely you can see that technology applied to planets.
Especially the details. I mean, you've got it's quite easy. It will correct it if you create a frame
I read it through, I use HR Pro, so different fields you can apply, I can apply all sorts of analysis as I can get.
Yeah. Well, it's very good.
But we were at the ASV meeting last, one of the guys from the planetary section had a shot of Mars, and the detail was incredible. I thought, hang on, is this Hubble Space Telescope? I think, I was thought he must have had like a 20 to 25 inch telescope together.
Yeah, and imaging, and more importantly, an absolute perfect
The detail was incredible. They even picked
Bear in
up.
mind that some amateurs literally spend well over $100,000 on their equipment, so you're really professionally just
They were picking up cloud details,
unbelievable.
which I thought was just absolutely incredible.
Because if you get it perfectly aligned and everything is right, so you can Okay, come on, give it a week. Stop. That'll be safe there for the moment.
Yeah, I think
I'll be getting back.
Yeah, we're going through
Do you want a coffee before you go?
That's just a very close. Nothing to do with sound paper.
Okay.
Just a
That's an old one, is it? Okay, cool. So I'll see you'll be next week's meeting?
Yeah.
Well, I've already
And,
finished.
and so I've listed it and taken off the $90 that I had in my credit.
Yeah.
Yeah, from,
Yep.
Actually,
Actually, I can do that. I'll write it down. You can sign for that.
you don't have to do it now.
That's fine.
Okay. You don't get any pieces, treasure.
Say,
No peace from your treasure.
know what the raffle box should.
Oh, the raffle box is around, that's been tailed away. I'll tell you what.
In the kitchen, there is.
Our treasurer is just over here.
Yeah.
It's the only way to be.
G'day Bob, how are you? Actually, I couldn't have been looking. Oh yeah?
I didn't finish something on the computer, so I finished it. Well, you've seen him talking years ago.
Yeah. Oh, you got the record to it?
Oh, put it up there.
Oh, I was there. What have you been looking at lately? Lousy weather.
Well, the west over there, we see it. So it's right.
I was there last Friday week.
Yeah.
I couldn't go last Friday.
Get your red torch, yeah. Not
Friday, this coming Friday. The weather is really crazy.
I'll preface this by saying the weather's disastrous. Whether we're seeing it, this remains to be seen. But we all know that. And anyway, even if you have a clear sky, you've got to hold the telescope down to the ropes anyway. Okay, it's got to get better. Anyway, for the morning sky, Saturn is not really at a high elevation, but perhaps it's because it's a wide-ranging graph. It has moved into the morning sky, and it can be seen in the dark part of it, as on the sky for the month handout. Jupiter's going up at a higher rate, so that probably will be higher in altitude than Saturn. Mercury is definitely out. There's my new sun as of last month, very yellow, and you can see Mercury belting around from this morning and virtually going right from our vantage point right into the sun, so Mercury is absolutely out for the viewing period. Venus is a goer back into the evening sky, but not really until after the end of September, but it's a goer. You can see by the increasing height, altitude from the sun. And that's simply Mercury on the 23rd of the 10th belting into the sun's glare from our viewpoint. Okay, and lastly, the planet, the month, the year, Mars, and please note that it's good. It starts to go gibbous at the end of this month. See how it's dropped in magnitude and it's showing a little sort of gibbous moon shape. It's going down. So get in quick. I'd say by mid-October it'll probably really start to drop in brightness anyway, whatever. And not a good idea to view it early-ish October. The moon. But doesn't stop you, but it could be a little bit of an inhibitor. Okay. The usual hemispherical charts. We have the messier objects declining now, and for those that don't like galaxies, yes, it's galaxy country rising. That's due northeast. So if you don't like looking at galaxies, search somewhere else, but it is galaxy country, coming up into the northern sky, northeastern sky, and similarly the southwestern sky. I mean, the sky changes through the year, and you have to go with the flow. Okay, within the constellation Pisces, that one there, I've just picked two simple objects, a double star up there, another double down there, and I'll show you those later. Similarly, for the southern sky, our messier objects are declining, the easy objects are going, many multiple stars are going, and we've got generally galaxy country slowly rising, but you can see the increasing density of the blue stars at the bottom, so the Milky Way is also nearly bottoming, and that'll be so for about, going through till 17th of October. It'll probably be right at the bottom by then. And then our lovely areas of Carina, Crux, Centaurus, Vela start rising again. And off we go again. Okay, I've picked two objects there to look at. I'll mention those later. One in reticulum and one in sculptor. Show you that later. Okay. Now, concentrating on two galaxies, not two galaxies, two constellations. On Sky for the Month, you've got the Sculptor constellation, which is not a terribly prominent one, but I'm trying to go through a few easy ones, and it has got good galaxies, and it has got lots of double stars. Now, just with reference to this sheet, there's quite a few double stars on this one. You've got Epsilon. Ooh. You've got Epsilon in the far corner. You can see it on your own. Don't put it down, it's not worth it. You've got Kappa up there, and I'll concentrate on two objects. One is an unusual cluster that I had a bit of trouble using the computer to find it, but it's near that galaxy, and it's near the star Zeta Sculptoris, which is that one there. Heaps of double stars there. They're on Sky for the Month, and the galaxies, if you want to look at them. Our Cigar Galaxy 253, that is so easy. It's basically 2/3 of the way from Beta Ceti, that red one up there, or the alternative name, okay? Beta Ceti, and the Sculptor star there. It's almost in deadline, and that is a very bright cigar-shaped galaxy. It's so easy. Another possible easy one is 7793, which appears as an elliptical haze. That is visible. Anyway, I've marked them all. The smaller the galaxy, in simple terms, the harder it is. So that's pretty hard. That one's a pretty bright one. So, if you like galaxies, go for them. If you like the double stars. There are also a couple of variables here. There's S Sculptoris in there, and there's R Sculptoris out here, a deep red variable. So, I'm trying to give variety. Okay. Escape from there and just show a blow up of a few objects. I'll get it right this month. I've actually got the right ones linked to this. Yay! Okay, the first one is a bit of a shot in the dark, but it's a fairly bright galaxy in Pisces that may be brighter than M74. It's small and its surface brightness is high, and even the amateur astronomers may not be aware of it. I'm not going to show you a deep and meaningful chart, but clearly, I mean, you're familiar with the outline of Pisces, and it's basically in here. I'll just give you the rough area, and you just go for it. That blows it up. It's at magnitude 10.6, so this is for these more serious people. It's in that area. Now, clearly you're not seeing it yet, but now you do. and that's exactly what it looks like. It's very condensed. It's got a very bright nucleus, which drops off quite markedly when it moves towards the outer halo. It's almost perfectly round and perfectly symmetrical. So if any amateur astronomer doesn't know about that one, it's claimable that a 6-inch will pick it up, so go for it. Okay, that's the only hard one. Now, in Pisces, there is a wide double. This is so easy. Okay, we're at the circle of the Pisces, okay? I think that's marked on the sky for the month. And the double, is up here. And it's not a true double, it's just a line of sight one. It's Kappa. Now, that's Kappa, the blue one there, I think. Anyway, they're blue and yellow. I'll do it on the... And it's claimed that any binoculars will pick it up. That's a better view of it. That's the top of the circle of the Pisces. Okay? That's Kappa, the primary. No, it's not the primary, it's just unrelated. They're just line of sight, and that's the one that it's close to, 9 Piscium. So, good contrast. I think that's magnitude 4 or 5, and that's magnitude 6 or something. It's on the chart anyway. Okay, that's so easy. And the next one is a little bit easy. This is on the other side. This is back to the inverted V of Pisces, going down the right-hand side. And it's down around here. And we're going to go to, how do you say it? Psi 1, Piscium. Okay. Radio, Psi 1, there it is, okay? And nice field at the left, but that doesn't help you find Psi 1. Now, it's claimed that with large binoculars, 11 by 80s or 15 by 80s, you can just start to split it. It's a true binary. They're connected. Okay? And they're equal magnitudes, fairly obvious. And if you get a small telescope, or if you've got, say, 20 by 80s, you might just see the magnitude 11.6 that makes it a ternary. Okay? So there you go. Psi 1 ternary. Okay, 2 to go. Southern sky. First one's the cheap ones that I missed last week, or last month, because I put the wrong thing on the computer. Now, this is a bit of a vague one, but this is in the constellation Reticulum, okay? And we're looking for a variable, R Reticulum. It doesn't really say much, all it does is show you where it is, and it's just a colourful field. I think there's 2 variables there. I think that's R Reticulum, and that might be another one in the constellation Dorado. No, not Dorado. Oh, I don't know. I've forgotten. Anyway, there it is. So it's quite a pretty field, and with a bit of luck, that's R Reticulum, which is a variable. Okay, last one. Charge. This is a bit of a shot in the dark. It's supposed to be a cluster in Sculptor. Now, back in Sculptor, it's near the galaxy 7793, and which is also near. It's a Zeta Sculpturus wide cluster. So if you can find Zeta Sculpturus, there's supposed to be a very large cluster that takes up 1.5 degrees. That the stars are supposed to be much brighter than magnitude 10, and I tried to use a computer to find it, but I wasn't so successful. That's sort of hinting at it, and that's hitting it a little bit better. The guy who made the reference is either lying or I can't find it, but that's perhaps a hint of it. It's supposed to be a very large cluster. Anyway, that's it, and it's time for me to escape.
Okay, well I guess Ian Sullivan next to talk about Mars. Does anyone else have anything to talk about after Ian? Okay. If If any of you wish to have a regular spot, either to give a talk or maybe lead a discussion or share something that you've read in astronomy or some other science subject every month, even if it's only for a couple of minutes, please feel free to come and see me afterwards, and we'll put you on as a regular to add a bit of variety to the evenings. Okay, thanks. Shut that down for me.
This is further to what I was talking about last time. For those of you who can remember, about Mars, we've been dealing with it for the last few weeks. And have you got the laser pointer, Peter?
Trying to find one for you.
I've got one, but it's in the projector box. I summarised these from some literature. There was also, I couldn't find it this week, but there was an issue of Time magazine in the last few weeks that had on the cover. You know, had Mars on the cover, and it was quite good. There was a lot of information, but they were concentrating on this sort of stuff. You see the first man-made satellite, Sputnik, you see in 1957. Russian probes failed to reach Mars in 1960. The first manned space flight by Russians and Americans in 1961. 1962, America's Mariner 2 passed within 35,000 kilometres of Venus and sent back photos. So it was Venus that was first seen by spacecraft. In 1962, that's the photos from Venus. Mariner 3 launch fails to reach Mars. 1965, that was the landmark first photos of Mars. There weren't a lot of photos, but there were some. It more or less dispelled the idea of the canals on Mars in 1965. And bear in mind, the Russians had tried all that time. The Russians tried all the decade of the 60s. They had very little success with Mars. They did better with Venus, but Mars they had nothing but trouble. 1969, the American moon landing. Of course, everybody was preoccupied with that. And Mariner 6 and 7 came near 3,000 kilometres of Mars, and more photos came through. And then 1971, Mariner 9 orbited Mars for nearly a year, photographing the two moons and creating a detailed map of the surface despite a global dust storm. The volcano Olympus Mons was discovered along with many dry martian riverbeds, once with flowing water, question mark. I heard a talk only yesterday about volcanism in the solar system and mentioned Olympus Mons. You notice that when you see pictures of it, it looks like a hole rather than a mountain, and the hole is in fact like a volcano. Those shield volcanoes, like the one in Hawaii, that's a classic one in Hawaii, which is a dome, it's a shape, shield. It gets the name shield from the Roman shield, which was curved. The idea of a gentle curve. The size of Olympus Mons is enormous. It's much bigger than the state of Victoria. So when it's double the height of Everest, you tend to think, oh gosh, that would be quite a climb. You think of climbing Everest, but it would be you'd climb Mount Olympus Mons with effortless ease. It would just take several weeks to climb it because the gradient is so slight that you're just going up. And then when you get to the top, you've got a collapsed, say it's not a cone type volcano like Mount Fuji. It's not like that at all. It's domed, and there's the orifice here, the caldera, is dropped away inside, and people don't quite appreciate that. But notice that there was several flybys, and it wasn't picked up till the early 1970s. The American Viking 1 and 2, of course, the big news of the mid-70s was the American Viking landing on Mars and getting the information and doing these experiments on life and taking photographs on the ground, on the surface. The situation is that there's a couple of spacecraft on their way to Mars. One's going to land in the middle of early January, another one like a couple of weeks later in January. So early next year we're going to get quite a lot of information to get on Mars, provided there's not a mishap. Now, remember the talk about we're close to Mars and we're not going to, we're 60,000 years, we're never going to be as close again and all that. So I got some information out of another source, and there are some figures. As you can see, back in 1956 it was the same as that. You see here, this doesn't show very well anyway. 1971, you see we got within just under 56 kilometres, 56 million kilometres from Mars. That should say million kilometres actually. Not kilometres. Million kilometres. August.
You've got September 27th. Should be August.
Oh, you're right too, yes. Yeah, it'll be August 27th there, yeah. But notice the dates there, that's an interesting point. Notice the dates are all around that same sort of time of the year.
Yeah.
Now, why would that be? Can you have an opposition of Mars any time of the year? You can. Well, why are these all that time?
Because the Earth is
Ah, yes. Because, see, the Earth reaches aphelion, which is furthest from the Sun. Anybody know the date?
It's opposite to 4th of January, isn't it? It's the opposite of 4th of January.
Well, 4th of January is what?
It's the closest.
That's the, what do you call that?
Perihelion.
Perihelion, yeah. So, the aphelion is July. It's American Independence Day.
July.
Yeah, so that means the Earth is furthest away from the Sun, and that needs to be, doesn't it? To get a situation having an opposition and be as close to Mars as possible, the Earth needs to be as far away from the Sun as possible.
Yeah, but you did have Mars as close as
Yes,
Earth,
that's half of the question. I've just got through the first half. The second half is what you say. Mars needs to be at perihelion. So Earth at aphelion, Mars at perihelion. Now the two don't line up. But in fact, Mars' situation close to perihelion, Mars perihelion is about August. So you see how August, line up in that sort of arrangement. So that's why you get, they're all around that sort of time.
Mars is more important because the Earth's orbit is closer to being circular.
Yes, that's a good point. Bruce has raised. You see, the Earth is from 147 million to 152 million in distance. That's only 5 million in 150, isn't it? Whereas Mars is like 207 as against 249. So there's quite a big difference, isn't there, between nearest and furthest. And so it's more important. So these are not all the oppositions. Remember, there's an opposition every couple of years. These are close oppositions. Right? That's what they are. And you see the distance there in million kilometres. And you see for 2003, and that's seconds of arc, the size. Bear in mind that Venus, when it's transiting the Sun, what sort of size would Venus be? In seconds of arc. Anybody know? No? Would it be more or less than that? More. Yeah. You see, Mars is around about the 55 kilometres. Venus will get as close as 35 million kilometres from Earth because of the fact that Venus, it's just its distance. We are closer. Venus comes closer to Earth than Mars will. That's where Venus is round. And we're both lined up with the Sun.
It's a bigger planet.
It's a bigger planet. It's a bigger planet than Mars, and it comes closer. So it gets up to about 60 seconds of arc, which is about a minute. So more than double the size of Mars. So you see, though, that in 2018, some of us will still be alive in 2018. It'll be only about less than a second, right, in size, what it is now. 2050 is pretty good. It's almost as much, isn't it? But,
why all the hype about this one?
Yeah.
The best 60,000 years when 2065 is clearly showing a most marginal difference.
2065, yeah. We won't live that long, but I mean, we're talking about, But what are they talking about 60,000 years? Yes.
Well, that's what the paper's going
around.
So
But however,
It's going backwards in time, though.
when you're talking about lots of time, of course, you imagine that position, the Earth perihelion and aphelion positions don't stay fixed. They slowly move around. And the same case with Mars. Now, there'll come a with Mars perihelion, just by the movements of the orbits, right? It's going to happen, it's so certain. But of course, even when it does happen, that doesn't mean that there'll be an opposition right at the right moment. The oppositions will happen when they happen. So you can get a theoretic, you can work out theoretically though what the distance will be, and it's not much less. I worked it out just using the figures, the aphelion, the perihelion figures, and it's only about 54.5.
Well,
So
there's
you see
54.7 in 2082, which is less than this year.
54.7, yeah, that's
But
right.
then the angular diameter is shown as less than for this year, which doesn't add up.
Well, that's the figures I got from this text. Yeah, it doesn't sound right. You see what you mean? Yeah. 54.7, 2082. That's, yeah, that should be slightly less than 54.7, yeah.
If that's 54.7, right, it should be greater than 20.
Yeah, it should be greater, shouldn't it? Because 54.7 is less than that.
Might be a mistake.
Yep, I'll have to check that one. Oh, that'll be the subject of my talk next month, isn't it? Yes, I see that one here, that I took them from the, when you look at them again, you can see that the situation here, right, 209, 24.7.
Anyway, that much difference in the fact that the angular diameter is roughly a third of a degree in field. And with decreasing apertures,
Now, what was that point again? What did you say? What, the angular diameter?
yeah, it's roughly constant with decreasing apertures telescope and computerisation will still be good use.
Yeah.
So what's the problem?
Yeah, the fact that that's big enough, does it matter that much, you know, that it's 1 second of arc smaller or something like that, yeah. It's not a major factor here. No, well, that's a fact now. Now, I had another overhead, but unfortunately it didn't make it here tonight. Well, I just noticed that I gave that Mars quiz last month, and President wasn't here. President wasn't here. He didn't come last month. Now, I reckon we'll give him the quiz tonight and see how he scores.
Gee, is that the time?
Is that fair?
We'll do the same to you next month.
Which English writer predicted the existence of 2 Martian moons in his novel Gulliver's Travels? No, only one person can answer, and that's the President.
Oh. Gulliver's Travels. Who wrote that?
Okay, he doesn't know it. Next.
You know who wrote Gulliver's Travels? Oh yes, I just heard it called out about 6 times. Well, first one he didn't get right. Number 2. Mars has 2 properties similar to Earth. One is its rotation on its axis. What's the other? Yeah, rotation on axis time, that is. What's the other?
Okay, next.
They're both revolving in the same direction?
Yes, but that's all the planets do that. That's not a big number.
No, Uranus doesn't. Uranus doesn't.
Yeah, but that's only 1 out of 8. Number 3, nearly half the Martian soil is an oxide of now silicon, iron, calcium, magnesium, aluminium.
It's iron oxide. Iron oxide.
You'd say iron.
Yep, mostly ferrous.
That's not correct.
So that's
Hey.
it's not 3.
Right, the largest peak on Mars is the volcano name.
Olympus Mons.
Right, he's got that one right. Number 5, Mars feature Sirius Major was discovered by a Dutchman in 1659.
Is that true or false?
No, what's the name of the Dutchman?
What's the name of the Dutchman?
1659.
1659.
Sirius Major was discovered by a Dutchman, famous Dutchman.
Huygens?
Huygens, correct. Number 6, Mars is a god of war, is a Greek or Roman god?
Roman.
Correct. Number 7, Deimos and Phobos are moons of Mars. What does the word Phobos mean?
Fear.
Correct. Number 8, rocket science received a boost in 1898 with the novel War of the Worlds, was published in that year. Who was its author?
H.G. Wells.
Correct.
First question, was that Swift, by the way?
Yes.
Yeah, it just came in.
Okay. Number 9, what gas makes up 2.7% of the Martian atmosphere?
2.7%.
2.7%.
Well, it's mostly carbon dioxide, so 2.7%. Well, maybe it's oxygen.
No.
Very low percentage.
But what's the other one? What's atmosphere?
Nitrogen.
Yeah, nitrogen, yeah. No, we have to be right. Number 10. Mariner 4 yielded the first close-up pictures of Mars in what year?
71?
No, first close-up pictures of Mars. I put it on.
Oh, did you? Mariner. No, pass.
No, well, let's see now. He probably wouldn't have beaten Yuck. I've got 7 right out of 10.
I've got 6.5.
6.5. It was about the same. It was about the same. So you might not have won last time. There we are. Right. So
It's a competition last time, wasn't it? Was it?
Yeah, I would like to.
Where's my book?
Okay. Who's next?
Okay, well, I think that's probably it.
Well, that was unexpected, really.
Is Marcus here? Is Marcus here?
Marcus. Anyone else have anything to say?
I just want to ask a question. Someone might be able to answer. A few weeks ago I noticed the moon was very high in the sky, like maybe 10 degrees from the zenith. Does anyone know how close it can get?
Yeah, well, you just got to add 5 degrees to the, effectively to the sun can get up to 75 degrees in altitude. So the moon can get about another 5 degrees more than that, so about 80 degrees. It can get up to about 80 degrees, yeah. So, yeah, that's pretty high, isn't it? And of course, don't forget the moon and sun are opposites. Remember, we think of the sun being highest in the sky in the summertime, the moon's highest in the sky in the wintertime.
Yeah, just one thing I might mention, a couple of novae were discovered over the last few weeks. One of them is very close to Epsilon Crucis, the fifth brightest star in the Southern Cross. That's the one that's not actually in the cross, but is in between two of the stars. And another one was discovered in the constellation of Skilton, which is pretty high up in the Milky Way. But unfortunately, with the weather we've had lately, I haven't had a chance to look at either of them. So I can't tell you much more than that at the moment.
What's the magnitude going to be?
But
What magnitude?
one of them's around about 9th, and the other one, I'm not sure what the latest is. I haven't seen anything on the one in Crucis for a while. But around about the same, I think, yeah.
Okay. Well, if there's nothing else, thank you very much for coming to the meeting, and we'll see you here
Mention
next month.
that Andrew Prentice coming next month.
That's my next sentence.
Yes.
Thank you. The speaker next month is Dr. Andrew Prentice from Monash University, which those who've been in the society a very long time may remember the last time he was down, a very, very long time ago, to talk about the formation of the solar system. And if you recall, he had a fairly radical theory around Laplacian waves of some variety, from what I recall, for the formation of the solar system that was poo-pooed for quite a long time, and I guess is still fairly contentious even today. So he'll undoubtedly be coming to tell us about that and what he's discovered along the way. So he's a mathematician by background, so he's strayed into astronomy and has obviously come across reactions from professional astronomers that would treat him as a mathematician, I would think. But he's certainly been very high profile, particularly when the Voyager and Pioneer spacecraft took their images of the outer planets and the moons around those planets. He was able to predict fairly well what the moon should be, or the native moon, not captured moons like Asteroid, but what the native form ones should be. So I imagine he'll be showing us all about that next month. Okay, well thank you very much everyone, and safe trip home.
Maybe.